So we finally got some data yesterday, and you'll be happy to know that there was no fire the second time I tried it. When I heated up the water and the oil started out around 90 degrees Celsius. The oil started out around 96 degrees Celsius. After it was allowed to cool for 10 minutes, the water's final temperature was 65 degrees Celsius, and oil's final temperature was 64 degrees Celsius. I'm going to help you with the calculations a little bit, but I'm not going to do everything, so some of this you're going to have to do on your own, and feel free to pause the video whenever you need to. For the first part, this is just a sample calculation. So they're showing you the equation. When they say heat released, it's Q, mass is M, specific heat is C, temperature change is delta T. And they just go through an example right here. They want us to calculate the heat released using your data for 75 milliliters of water. So we're going to be solving for Q. We've got M and C and delta T. So the mass of the water, well, we know it was 75 milliliters. What we've learned about the density of water means it's also 75 grams. So we're going to plug in 75 grams for M. C is that specific heat capacity. It is given up here. It's 4.18 joules over grams degrees Celsius. And then our delta T is temperature change. And if you look at the data for water, it went from 90 down to 65. So if we were to subtract 90 minus 65, we get 25 Celsius degrees. And actually you can write it either way, degrees Celsius or Celsius degrees. It doesn't matter. Make your units cancel, grams cancel, Celsius degrees cancel. You're left with joules. So you're going to multiply those numbers together, and you're going to put your answer in here. And since 75 grams has 2 sig figs, your answer should also have 2 significant figures. All right. To the next question. You're actually going to do the same calculation, except this time you're going to do the mineral oil, and you're actually going to do that on your own. So same equation, Q equals MC delta T. Assume that the mass is also 75 grams. They give you a different specific heat value, and then you're going to calculate your own delta T. Pause the video if you need to. Right. Yesterday, Holly and Cherish and Zach redid this part of the lab for us, and they got some really good data. So I'm going to give you the numbers and go through the calculations with you a little bit. We've got the initial temperature of water was 60 degrees Celsius. They added that water to ice, and they stirred it, and it ended up being 0 degrees Celsius, which means that the water temperature changed from 60 to 0. It changed by 60 Celsius degrees. The final volume of the cold water, so if you are wondering where these numbers came from, I'd like you to pause the video and ask any one of the 3 people who worked on this, Cherish, Holly, or Zach. The warm water started at 30. Because one thing you might be wondering is why was the cold water 57 and the warm water only 30? They should be able to tell you that. This is also a hint right here. The volume of water from melting ice. This means that 27 milliliters came from the melting ice. The mass of the ice melted. Well, we know that the density of water is 1 gram for every 1 mil. So 27 milliliters is also 27 grams. The first calculation, you are going to use the same one we did before. Solving for heat, we know we usually call that Q. So I'm going to help you get set up right here. It says use the original volume of warm water in the calculation. So we have the warm water, which was 30 milliliters. And actually, we know that was also 30 grams. So let's put a G in here. And then we have our C value, which is 4.184. And those units are joules over grams times Celsius degrees. And our temperature change, our warm water went from 60 to 0. So that's a delta T of 60. Our grams will cancel. Our Celsius degrees will cancel. When you multiply these numbers, you are going to get an answer with the units in joules. And you can write that right here. Pause the video if you need a minute to multiply that out. Right, so let's see, this is out of order. This is the slide that I want. So in this next part, you're going to calculate the heat of fusion of ice. And I looked in the lab, they didn't really give you this equation, so I'm going to go ahead and give that to you. Q always means heat, and when you're going through a phase change, you do a different kind of equation. You still do the mass, except you do something called heat of fusion. And we're actually solving for heat of fusion here. So we're going to rearrange this equation. If we want to solve for heat of fusion, then we need to get it by itself. So we're going to divide both sides of this equation by mass. So we are going to do Q over mass. And if you read up here, they say take the answer to calculation A and divide that by the grams of ice melted. So if you look at your data table, you should see that 27 grams of ice was melted. And when I did the calculation in part A, I got 7,500 joules. So hopefully that's what you all got. I did round to 2 sig figs because my data had only 2 sig figs. So you're going to want to divide those, and then you see that joule per gram is our unit. And you're going to get a number here. And I'll let you go ahead and divide that and write your number in. Pause if you need to. The final thing you're going to do is solve for percent error. The theoretical value is like the true accepted value that gets plugged in here where it says theoretical. Experimental, whatever you get right here, goes there. You know that these mean absolute value, so when you subtract those, if it's negative, you're just going to make it positive. And then you're going to get a percent error value right here. So you're all going to want to calculate that on your own. And pause the video if you need to. I'm going to give you just a few hints on these questions. A lot of you got these first ones answered already. Why is water called the universal solvent? It was on page 4-1 of your experiment. A lot of these questions are answered in the introduction, so it's always a good idea to go back there. Also 4-1 for surface tension. Why did floating sulfur sink when detergent was added to the water? I want you to think about what happened to the surface tension when the detergent was added. Did it decrease or increase? So think about surface tension for this. And then also think, did it increase or decrease? And you know that because of what happened to the sulfur. Define a hydrate. That definition was on 4-2. A lot of people are asking me about number 4. You're going to go to part B under solubility. And the question you should be asking yourself is, when was the KNO3 dissolved? Was it when the water was hot, or when you put the test tube under the cold water and it went back to a solid? So does hot water make a solid dissolve, or does cold water make a solid dissolve? And that will help. That way you'll know about the temperature. So solubility means amount that will dissolve. So more soluble means more will dissolve. Less soluble means less will dissolve. All right, next question is, which dissolve faster, the large or small crystals? That's in solubility part A, where you dissolved the fine salt and the rock salt, that was bigger pieces. And you're going to want to use the word surface area to explain this answer. Just put that in here, surface area. Okay. Number 6, from your results, compare the number of calories released by the water and the mineral oil. You're just going to tell me which liquid released the larger amount of heat, so just look at your calculations. It's going to be mineral oil or water. And then given in the question are the specific heat values. You just have to find those and tell me which one was higher. Number 7, heat of fusion. It's on 4-2. Number 8, think about why our answer wasn't perfect and what source of error could have been present. And all right, so number 9 asks why steam at 100 degrees Celsius causes more serious burns than liquid at the same temperature. And this might seem a little bit strange, but there's actually more energy in the 100-degree steam than the 100-degree water. So I'm going to do this one with you. There's more energy. And the reason for that is that the steam actually gained more energy during the phase change. So you have to put energy into the water to get it to go from liquid to gas. And that extra energy actually causes the steam to cause a more serious burn than the liquid. The final question is a pretty lengthy calculation. And we're going to just do this whole one together. So in Chem 1, we learned about heating curves, and they are something that looks like this. And down here we have step 1, and this is when we have solid, and in this case it's ice. So the first thing you have to do is you have to add heat to melt the ice. then you have to heat the liquid. And then you have to put energy in, and this would be part 2. And then you have to put energy in to change the liquid to gas. And that will be, and actually this is a phase change. It's solid to liquid. I should clarify that. And this is another phase change. This is where you go from liquid to gas. So you actually have both phases present at that time. So at part 1, actually all 3 parts you're going to solve for Q. And remember we said that was heat. Part 1 is called, you use something called the heat of fusion. And so the heat needed to go through this phase change is equal to the mass of the substance times the heat of fusion, which is unique for every substance. And this is going to be the heat of fusion of ice or water, and we see that's 334. We also see that we're working with 20 grams of ice. So we have 20 grams times 334, and those units are joules over grams. It's nice to put the units in because your grams will cancel, and then you know that you just have joules, which is a good unit for Q, or heat. When I multiplied those out, I got 6,680 joules. Then we have part 2. And part 2 is probably the equation we've used more. It's the mass times C times delta T. And we said that C is the specific heat capacity. And it's also unique for every substance. We still have 20 grams, so our mass has not changed. It's going to be the same throughout the whole problem. We now have water, and the specific heat of water is 4.18. And those units are joules over grams degrees Celsius. And then delta T. And you may be thinking that they don't give us enough information, but they actually do. So we know that ice is at 0. And we know that they're heating it all the way to steam at 100. So we've got a delta T of 0 to 100, which would be 100 Celsius degrees. And so cancel out all the units that you can. You know you're doing it right if you get joules for your unit that's left over. 20 times 4.18 times 100 is 8,360 joules. And then finally part 3 is the energy required to change the liquid water to a gas. So we're back to an equation that looks a lot like number 1. It's going to be M, and this time this one's called heat of vaporization, not heat of fusion, because we're going through a different phase change. So the mass still 20 grams through the whole thing. The heat of vaporization is 2,260. And when I multiply those, I got 45,200 joules. They do ask for the total quantity of heat. There are 3 different parts, so all you have to do is add all these up together. So this part plus this part plus this part, that is your answer. I'll let you all do that part on your own. Make sure you put unit of joules, and you should be done with your lab report. It's very important that you turn this in on Friday. I'm going to come in after school, collect them, grade them, put them in the computer for Dr. Peralta. But I I don't necessarily want you to turn it in on Thursday because you have your quiz on Friday. Hope this made sense.